We need to do this. Oh, 26 cards? Dude, are any of these like... What? That's so many. Alright, let's do it. Ah. I looked up the meaning of imperative, and I can't remember it anymore. But there's a declarative and an imperative. Imperative is saying exactly what you want and exactly how to do it. Certain operations in a certain order. 2.4 months gone. Impedance mismatch. Oh shit. Was this impedance mismatch? Shoot. Let's see. I can't remember what this is. Okay, so it's not encoding decoding. I don't think it's that. So my next guess would be... Oh, thank you. My next guess is just going to have to be... encoding, decoding... Come on, where is it? I can't remember. Dang it, bro. Dang. When the data models and the application do not match the storage models, okay. Schema on write is what we usually think of like a relational database. It's predefined. It has defaults. I don't know. Schema is explicit, and all the written data conforms to it. Okay, so that's good. Normalization and denormalization. So normalization reduces it reduces the Okay. Normalization is using pointers to point to the same data. You can pre-fill stuff and have higher quality. Also, searchability. Because consistency is higher. Denormalization means the same data is stored in multiple places. This provides locality, so maybe faster reads, but at the cost of consistency. Yeah. Update complexity, yeah. A covered index is when some fields are stored next to the index, commonly used ones. This has come up so many times. An SS table is a sorted string table backed by an in-memory data structure. Sorting makes compaction and merging much easier. A cluster index is when the data is stored directly next to the index. A message broker. Read this. A message broker is an intermediary. It can act as a queue or a buffer, and it gets rid of the request response contract, and it also sits in between. I said that already by saying it's an intermediary. There was one more point to make about it. Acts as a queue buffer. Oh, and it abstracts the final destination. So JSON, XML, and CSV are widely adopted and human readable, but they're very ambiguous and they don't support binary encoded strings. Binary strings. And there's no schemas, that's right. The actor model. The actor model is where Each actor has its own state, isn't aware of the other. It can send messages, but none are guaranteed. And it's a programming model for concurrency. Compatibility. Oh, when we talk about encoding and decoding, if what encodes the data and decodes the data works, then it's compatible. The relationship between one process that encodes the data and another that decodes it. Okay. The pros and cons of binary encoding are, pros are you can save space, and therefore it's faster. The cons are it's not human readable, more complex, and you have to worry about forward backwards compatibility. Oh, and then you have to get buy-in, yeah. A distributed actor framework. Is the actor model, but applied to distributed systems. It's how we might scale them, and each service is acting on its own, similar to the actor model. Location transparency. This is like, it's kind of like a programming model where we pretend like network calls are just function calls within our service. We abstract the network call away. The merits of schemas. Schemas are sick because they provide a number of benefits. Code generation, a form of documentation. Predictability, static typing. Oh, and then you can binary encode them. Can be more compact, yeah. Statement-based replication. Ooh, this is a tough one. Statement-based replication is when we take the statement that was used to produce the resulting state. The problem with this is if the record has non-deterministic data in it. Catch-up recovery is you diff from your last write with the leader, write them, and then you're caught up. Consistent prefix reads. I think is like whatever the order the data is written in is the order that it's read, or that is the order that it's returned. Yeah. Monotonic reads is a guarantee that once you read one state, you'll never read an older state. You'll only ever read newer states. multi-leader configuration is when you have multiple leaders, which means multiple replicas that you can write to, and each replica acts as a follower to the other followers, and it broadcasts its updates. Has to forward that to the other leaders, yeah. Read after write consistency is when we, as a user, we write to a replica. We should always read from that replica. Well, we shouldn't. That's not necessarily the way you have to do it, but once we write to a replica, we should always see our data reflected. It shouldn't look like it's missing after a successful call. Yeah. Write ahead log shipping is you maintain a wall and you use that to update replicas. Yeah, backwards forward compatibility with this. Okay. Some replication log implementations are oh, write ahead log shipping, statement based, row based, so you literally just store the rows, and then I did statement wall row. I forgot the last one. Logical and trigger based. You programmatically define the replication logic. It's a cop out. Trigger based is where you have a custom layer of logic where you define the replication logic. Yeah. Leader based replication is, I'm not sure, where we have all the writes go to one replica and all the reads go to the other replicas, and the leader will tell the followers about new data. Yeah, nice. Failover is when the leader fails. We need to define a new leader, get all followers to now get data from that leader. We need to tell everybody to talk to that leader. And when the old leader comes back online, we have to tell it it's now a follower. What a doozy, huh? What a doozy. A conflict is in a multi-leader setup when the same record is updated or written at the same time. Once we try and replicate, there's conflicting states. Yeah. A few examples of multi-leader replication. Google Docs. Multi-regional database setups. There's one more. I mean, like GitHub. Oh, a calendar. offline application. Yeah, offline application functionality, like a calendar. Nice. Avoid conflicts altogether. Then you have most recent write wins. Uh, highest ID wins. Higher number of replica wins. Concatenation. And then prompt the user for resolution. Okay. So multi-leader, it's faster. You failover is more likely to succeed. I don't know if that's true. I don't know if that's true. Let's see, pros and cons. So pros would be faster write speeds, geographical locations, less vulnerability to network issues, and less vulnerability to, I guess, just regional failures because you're multi-regional. Cons. It's really complicated and you have to deal with conflicts. I remember those. Faster writes, no more bottleneck, and you're resilient to outages, and better internet resiliency too. Replication topology describes the map of replications, the communication paths along which writes are propagated from one node to another. Okay. Nice. Oh, that was so many cards, dude. Jeez. That took a long time. Ugh. I only have a few. This is why it's starting to take so long. I'm like spending no time actually reading anymore. I wonder. All right, so the sections: leaderless replication, write to the database when a node is down, read, repair, and anti-entropy. Quorums for reading and writing, limitations of quorum consistency. So I assume leaderless replication implies everybody can read and write. Opertion. Huh? The replication approaches we've discussed so far in this chapter, single leader and multi-leader replication, are based on the idea that a client sends a write request to one node, the leader, and the database system takes care of copying that write to other replicas. A leader determines the order in which writes should be processed, and followers apply leaders' writes in the same order. Some data storage systems take a different approach when abandoning. No. Some data storage systems take a different approach, abandoning the concept of a leader and a follower. What am I reading? Alright, it's fine. Some data storage systems take a different approach, abandoning the concept of a leader and allowing any replica to directly accept writes from clients. I cannot. Well, some of the earliest replicated data systems were leaderless, but the idea was mostly forgotten during the era of dominance of relational databases. It once again became a fashionable architecture for databases after Amazon used it for its in-house Dynamo system. Dynamo style. In some leaderless implementations, the client sends its writes to several replicas, while in others, a coordinator node does this on behalf of the client. However, unlike a leader database, the coordinator does not enforce a particular ordering of writes. As we shall see, the difference in design has profound consequences for the way the database is used. So let's see here. There should be let's see. Let me Google this real quick. Oh no. No. Alright, whatever, later. Let's see. Back here. So Imagine you have a database with 3 replicas and one of the replicas is currently unavailable. Perhaps it's being rebooted. In a leader-based configuration, if you want to continue processing writes, you may need to perform a failover, right? On the other hand, in a leaderless configuration, failover does not exist. The client sends the write to all 3 replicas in parallel, and the 2 available replicas accept the write, but the unavailable replica misses it. Let's say that it's sufficient for 2 out of the 3 replicas. I see. They did this because they didn't want to miss any data, right? This would mean that your write always makes it to a replica. And then if a conflict somehow arises, you have all the data, right? Let's say it's sufficient for 2 out of 3 replicas to acknowledge the write. After user 1234 has received 2 OK responses, we consider the write to be successful. The client simply ignores the fact that 1 missed. Yeah, because it doesn't matter. It's like, yeah, now it's quorum. Now imagine that the unavailable node comes back online, the client starts reading from it. Any writes that happened while the node is down are missing from the node, thus you read from that node. You may get stale, outdated data value as responses. To solve that problem, when a client reads from the database, it doesn't just send its request to 1 replica. Read requests are also sent to several nodes in parallel. The client may get different responses from different nodes, i.e. the up-to-date value from one node and a stale value from another. Version numbers are used to determine which value is newer. Okay. The replication scheme should ensure that eventually all the data is copied to every replica after an unavailable node comes back online. How does it catch up on the writes that it missed? 2 mechanisms are often used in Dynamo data stores. Read repair. When a client makes a read from several nodes in parallel, it can detect any stale responses. For example, so a read can result in a write. For example, in figure 5.10, user 2 gets a version 6 value from replica 3 and a version 7 value from replicas 1 and 2. The client sees that 3 has a stale value and writes the newer value back to that replica. This approach works well for values that are frequently read. Okay. Anti-entropy process. Sounds like something out of a sci-fi film. In addition, some data stores have a background process that constantly looks for differences in the data between replicas and copies any missing data from one replica to another. Unlike the replication log, I don't like that. Unlike the replication log and leader-based replication, this anti-entropy process does not copy writes in any particular order, and there may be a significant delay before data is copied. Not all systems implement both of these. For example, Voldemort currently does not have anti-entropy. Note that without an anti-entropy process, values that are rarely read may be missing from some replicas and thus have reduced durability because read repair is only performed when a value is read by the application. Okay. Uh, um, In the example of figure 510, we consider the write to be successful even though it was only processed on 2 out of 3 replicas. What if only 1 out of 3 replicas accepted the write? How far can we push this? If we know that every successful write is guaranteed to be present on at least 2 of the 3 replicas, that means at most 1 replica can be stale. Thus, if we read from at least 2 replicas, we can be sure that at least 1 of the 2 is up to date. If the 3rd replica is down or slow to respond, reads can nevertheless continue returning an up-to-date value. More generally, if there are n replicas, every write must be confirmed by W nodes to be considered successful, and we must query at least R nodes for each read. In our example, n equals 3, W2, R2. As long as W plus R, write plus read, is greater than n, we expect to get an up-to-date, so 2 plus 2 is 4, greater than 3, cool. To get an up-to-date value when reading, because at least one of the R nodes we're reading from must be up-to-date. Reads and writes that obey these rules, values, are called quorum reads and writes. You can think of R and W as the minimum number of votes required for the read or write to be valid. This doesn't sound right. Hmm. It's not right. This is what we need. In Dynamo-style databases, the parameters NWR are typically configurable. All right. 18 seconds left. Okay, so I would like, just quickly, I would like to get ChatGPT hooked up, because it can act as like, it can read what I wrote in certain sections, and like, what if I go back and fix some of those flashcards using ChatGPT? You know what I mean? Could be better. Anyway.